Lecture 3, Eulerian circuits, vertex degrees and counting. Recap of previous lecture. In previous lecture we have discussed the useful properties of connection, paths, cycles, walk, and how the statements in a graph theory can be proved using the principle of induction and the principles of contrapositive and so on. Now, content of this lecture. In this lecture we will discuss Eulerian circuits, the fundamental parameters of a graph, that is the degree of the vertices, counting and extremal problems. So, Eulerian circuits background, if you recall, it is about the Königsberg bridge problem. So, the famous mathematician Euler himself has given these particular proofs and ideas. So, we will see here in this part of the discussion, so how that particular Königsberg bridge problem which was posed and how this particular problem was solved by systematically going through all the background, that is the definitions, and then finally in the end of this particular lecture we will be stating up the theorem which himself Euler has given, and but the proof Euler could not give. So, another mathematician Howard has given the proof. So, we will be looking up that proof in the end of this particular Euler's theorem. So, let us begin with the Eulerian circuits. So, a graph is Eulerian if it has a closed trial containing all the edges. Trial, we have already given the definition that trial is a walk in which the edges should not repeat. If the edges are not repeating in the walk, that does not mean that the vertices are also not repeating. Vertices can repeat, and that particular walk in which only the edges should not repeat, that is called a trial. A closed trial means from the point where it is starting, if it is finishing that trial, it is called a closed trial. So, a graph is Eulerian if it has a closed trial containing all the edges. So, we call a closed trial a circuit when we do not specify the first vertex, but keep the list in a cyclic order. So, an Eulerian circuit or a Eulerian trial in a graph is a circuit or a trial containing all the edges. Let us take some more definitions. So, an even graph is a graph with the vertex degrees all even. So, if all the vertices having an even degrees, then that graph is called an even graph. A vertex is odd when the degree is odd or even. So, our discussion of Eulerian circuit applies to the graphs with the loops. We extend the notion of the vertex degree to the graphs with the loop by letting each loop contribute 2 to the degree of its vertices. So, this discussion, as far as Eulerian circuit is concerned, Eulerian circuits are basically applicable on a multigraph as well. So, what is a multigraph? So, as you see that the graph which has basically the parallel edges like this is called a parallel edge, or the graph which it contains the loops, this particular graph is called a multigraph. Whereas in the regular or simple graph, these parallel edges are not there and loops are not there. In this Eulerian circuits, we will assume that the graph is given in the multigraph. Why? Because the problems which you have seen in the Königsberg bridge problem, similarly the mail transfer problem in which a postman delivers the mail on both the sides of the street, will form basically the multigraph, and this particular problem is basically having lot of practical relevance to establish whether the closed trial containing comprising all the vertices, that is called Eulerian circuits, are present in the graph or not. Take the example. That if let us say there is a city and The mail courier basically starts from this point, visits these set of houses, then go and visit these set of houses, and then visits these set of houses, these set of houses, and return back to the same point. This particular kind of map of a particular locality can be represented in a form of a graph. So, where the vertices are present at all the intersections like this, and for each side of a street we can put an edge, and when we complete this it will form a particular graph. So, this graph is basically a multi-graph. Now, the question would be whether this multi-graph is an Eulerian graph or not. So, if it is Eulerian graph, then Euler circuit must be present in this particular kind of graph. So, that is why we say that this discussion, that is the Eulerian circuits, when we discuss, it will include the multi-graphs, because multi-graphs are present in most of the scenarios which we are going to use it for our different applications. So, let us see some more definitions and then we will go ahead. So, maximal path, a maximal path in a graph is a path P in that particular graph G that is not contained in a longer path called a maximal path. So, when a graph is finite, no path can extend forever. So, a maximal path exists in a graphs which are finite, and that we are going to consider in our case, that in the graphs which is finite there exists a maximal path and we will use it in the extremal conditions. So, let us see the lemma which states that if every vertex of a graph G has the degree at least 2, then that graph G contains a cycle. So, let P be a maximal path in a graph, and let assume that U be the end point of that particular path. So, this is a maximal path. Maximal path is obtained by as we add the vertices, it will keep on growing the path, and finally a stage will come when you cannot extend the path further. So, that becomes a maximal path, and let us assume that this P is a maximal path in a graph G. Now, since this particular maximal path cannot be extended, so every neighbor of U, so neighbors of U must already be the vertices of this particular path P. Now, since U, this particular node has the degree at least 2 from the statement, so it has the neighbor, let us assume V, in this particular vertices of a path via an edge which is not in P. This particular edge is not there in P. Hence, this UV edge, which basically will incident on U to increase the degree to 2, this edge UV and also the remaining portion of a path which is connecting U and V, that is UV path, portion of a path P which is containing UV path plus E together will form a cycle. So, hence this particular theorem will prove that if the graph G has the degree at least 2, then the G will contain the cycle. Now, this is the important theorem which is given himself by the Euler, but the theorem Euler could not prove it. So, another famous mathematician has proved this particular theorem after several years of basically existence of this particular theorem. Proof came quite late. Let us see this important theorem which states that a graph G is Eulerian if and only if it has at most one non-trivial component and its vertices all have even degrees. Now, this particular theorem will characterize the graphs, the class of graphs, that is the Eulerian graph, with the properties which is stated on the other side, that it should have at most one non-trivial component and its vertices all have even degrees. This particular property is very important to characterize a particular graph as an Euler graph. So, let us see first the necessity part of this particular condition one side, which states that a graph G is Eulerian only if it has at most one non-trivial component and its vertices all have even degrees. So, that means that if you are given a graph as Eulerian graph, you have to prove all these properties. It will imply all these properties, that it has one component, it has non-trivial component and all its vertices have the even degree. So, let us suppose that G is a given graph which contains an Eulerian circuit, and let us call that circuit as C. Now, this particular circuit C, when passes through the vertices, it uses two incident edges. For example, if this particular vertex, if that circuit passes, C passes through it, so it will incident through one edge and it will exit out from another edge of this particular cycle. Now, and also the first edge and the last edge, first edge is paired with the last edge at the first vertex, hence every vertex has the even degrees in this particular case of incidents when the circuit passes through the vertices. Also, two edges can be in the same trial only when they lie in the same component. So, there is at most one non-trivial component. Now, we are going to see the sufficiency condition states that other side of the proof, that if G is Eulerian, if it has at most one non-trivial component, on all its vertices have the even degrees. So, that means now we will assume that this particular condition holds. Which condition? That it has at most one non-trivial component and its vertices all have the even degree. So, let us assume that this particular condition holds and we obtain an Eulerian. Now, we have to obtain an Eulerian circuit using the induction on the number of edges m. So, when m is equal to 0, that means number of edges is 0, that is called a base step of the induction. So, we will see that in a closed trial consisting of one vertex will suffice. Why? Because there is no edge, hence this will be considered as an Eulerian circuit. Now, this particular induction hypothesis, let us assume that it is true for m is greater than 0. With even degrees, every vertex in a non-trivial component of G has degree at least 2. Now, by lemma 1.2.25, the non-trivial component has a cycle C, that we have already seen in the previous lemma, that if the degrees are at least 2, then it must have a cycle in a non-trivial component. Let us assume that the cycle is C, which exists. Why? Because we have seen that particular degree at least 2. Now, let us remove this cycle from the graph G and we will obtain a G prime, be a graph obtained from G by deleting that particular cycle. So, G prime is nothing but G minus E of C. So, here in this particular example, if this is G and this C is cycle which is shown as a dotted, if you remove it, what will happen? It will be broken into component 1, component 2 and 3 components will basically be available once it is deleted. Now, since C, that is the cycle, has 0 or 2 edges at each vertex, so each component of G prime is also an even graph. Why? You can see that this particular vertex which touches this particular cycle, it has the degree 2, the other vertices which are not touching this particular cycle has degree 0 here in this particular cycle. So, C has 0 or 2 edges at each vertex. So, each component of G prime is also an even graph. Now, since each component is also connected and has fewer than m edges, we can apply the induction hypothesis to conclude that each component of G prime has an Eulerian circuit. Okay, so, this particular components have an Eulerian circuit. Now, further on, to combine these into the Eulerian circuit of G, we traverse C, but when a component of G prime, so this is one component, this is one component, 2 component, 3 component. But when a component is entered for the first time, we detour an Eulerian circuit of that component. Let us take the example. We are basically traversing through the circuit of G, and once we enter for the first time in this component, we detour this particular component and come back to the same point, and then go ahead. When we enter for the first time to the second component, we detour and come back to the same point, and when we enter for the first time third component, we detour, and so on. When we enter here the fourth component, this is the fourth component, we come back to the same point, detour, this component is already visited, and we come back again to the same point from where we have started. This completes an Eulerian circuit of G, the way we have detoured it. So, hence what we have proved here is that we started by assuming that this particular condition holds, and now we have obtained a Eulerian circuit, hence this particular graph is Eulerian, that we have proved. So, both sides we have completed the proof. Now, this particular theorem will characterize the graphs as Eulerian graphs. So, in the characterization of Eulerian circuit, the necessity of the condition is easy to see. It is also holds for the characterization of bipartite graph by the absence of odd cycles and for many other characterizations. So, all these characterizations will basically make the equivalent statement, and we are using them in our theory, the graph theory. Nash-Williams and others popularized a mnemonic for such theorem called Tonkas, meaning that the obvious necessary conditions are also sufficient. Extremality. So, the proof of lemma 1.2.25, in which we have used the maximal connected subgraph or the maximal path, that is an extremal condition, is an example of an important technique of a proof in graph theory, and we call it extremality. When considering the structures of a given type, choosing an example that is extreme in some sense may yield useful additional information. For example, since a maximal path P cannot be extended, and this property we have used in the previous theorem proof. So, this particular extra information that every neighbor of an endpoint of a P belong to the path, why? Because it cannot be extended further. So, this extra information is utilized in the proofs of the theorem, and this is called extremality property, and that we have used it. Now, let us see the proposition. If G is a simple graph in which every vertex has the degree at least k, then G contains a path of length at least k. Now, if this particular k value is greater than or equal to 2, then G also contains a cycle of length at least k plus 1. Let us see the proof quickly. Let U be an endpoint of a maximal path. So, we will assume a maximal path P and U be the endpoint. Now, since P cannot extend, so every neighbor of U will be in Vp. Now, since U has at least k neighbors, and G is a simple graph, so P therefore has at least k vertices other than U and has length at least k. Now, if the k is greater than or equal to 2, then the edge from U to a farthest vertex to a farthest neighbor, let us say V along P, this particular edge along P completes a sufficiently long cycle with a portion of P from V to U, and hence basically both the conditions we have proved this particular proposition. Now, let us see the important notion of the degrees and their properties and some important lemma that is called a handshaking lemma based on this particular property of a graph. So, the degree of a vertex V is written as d of V. Since for the graph G we are talking about, so we have to write down G for it. Only one graph is basically considered in the problem, then we straight away directly write dV means the number of is a degree of a vertex. Degree of a vertex means the number of edges which are incident to that particular vertex. So, degree is nothing but the number of edges which are incident to that particular vertex. So, if this is the vertex, how many edges which are incident? This is edge 1, this is edge 2, edge 3. So, the degree of this particular vertex is equal to 3 in this case. Why? Because 3 edges are incident to this particular V, except that each loop at V counts twice. For example, if loop is also there in a multi-graph, then it will count 2 to it. So, the degree then becomes 5 here in this particular case. So, having defined the degree, then now we have to see another property of a graph. This is called a maximal degree. So, a particular vertex having the maximum degree will become a property of the entire graph called a maximum degree of a graph, and is represented by this symbol big delta of G. Similarly, a particular vertex which is having the minimum degree in the graph will basically also induce a property into a graph that is called little delta of G, is called a minimum degree of a graph. These are the properties of the entire graph. So, here in this particular example we can see that the degree of B is 3, degree of C is 2, and there is no other vertex which is having degree more than 3. So, hence the maximum degree of this graph is 3 and C has degree 2. So, no other vertices is having degree less than 2. So, obviously the minimum degree of a graph will become 2 here in this particular case. Now, for a regular graph, now if G is a regular graph, then this property holds that the maximum degree is equal to the minimum degree of a graph. Now, if G is a k regular graph, then basically this particular common degree is equal to k. Now, the neighborhood of a graph is represented by ng of V or n of V, is nothing but the set of vertices which are adjacent to V. For example, if this is vertex V, so let us say this is U1, this is W1, Z1. So, the neighbors of V will be these set of nodes. Now, you see that the degrees of all the nodes is 3 here in this case, that is why this graph is a 3 regular graph. Order and size of a graph. So, order of a graph is written in this particular form ng. that is nothing but the total number of vertices which are present in the graph is called order of a graph. Similarly, the size of a graph is nothing but the total number of edges which are present in the graph called size of a graph. And the notion, the order of a graph, we can represent through the indices 1 to n. Now we have to, using the degrees of a graph, we will see a important proposition or important lemma that is popularly known as handshaking lemma. So this proposition is called degree sum formula, which is stated as, so if G is a graph, then summation of the degrees of all the vertices in G is nothing but twice the number of edges in the graph. So let us see the proof. Now if we sum the degrees, then so this is the particular vertex V1 and this is particular vertex V2. So whenever we are summing up the degrees of a particular vertex is nothing but the edges which are incident on that particular vertex. Similarly, this edge is incident on the other side of a vertex also, other side of the edge, that is also another vertex. So every edge is incident on two vertices. So hence the degrees, when you are sum, is being counts each edge in a 2 times. Hence each edge has 2 ends and contribute to the degree at both the ends. Hence when we come up with the degree sum, that means we have ended up counting the edges 2 times. Hence this becomes a handshaking lemma. It is also called degree sum formula. If you want to see the example, let us take this particular graph which is having 3 vertices A, B and C, and there are 2 edges. 2 edges means total number of edges are 2, 2 into 2, that is 4. And if you count the number of degrees, so this particular, the degree of vertex A is 1, degree of vertex C is also 1, degree of vertex B is 2. So that becomes, degree sum will become 4. So sum of the degrees of all the vertices is nothing but twice the number of edges. How many edges are there? 1 and 2, there are 2 edges. So hence this particular theorem is always proved. So if you count the total number of degrees, if you count the degree sum of a particular graph, you will end up with the twice the number of edges which are present in the graph. So this handshaking lemma has given some important corollaries. Let us see them. So in a graph G, the average vertex degree is 2e by ng. So 2e means degree sum is nothing but 2e and divided by total number of vertices, that becomes the average vertex degree of a graph. Now this degree of a graph is at least the minimum degree of a graph and basically at most the maximum degree of a graph. Hence this corollary is proved. The second corollary states that every graph has an even number of vertices of odd degree. So every graph has an even number of vertices of odd degree. Now you know that sum of degrees of vertices in a graph is twice the number of edges of a graph, and this is an even number. So degree sum is an even number. So there are 2 types of, or there are 2 parities of the degrees in the graph. One is the even degree, the other is the odd degrees. So the even degrees, whether you multiply with even number or a odd number, this particular factor will become an even number. In the odd degree, it has to be a even number to be multiplied, so that the entire component will become even, which is same as the other side. So, how many? So, that means some even number is to be multiplied. So, even number of, that is how it says that. So, every graph has an even number of odd degrees, and hence the corollary proves, and no graph of odd order is regular with the odd degree. This is straightforward, we can obtain. Another corollary which says that a k regular graph with n vertices. So, k regular graph with n vertices, what is the degree sum? Kn, and that will count twice the number of edges. So, if you want to find out how many edges are there, then you divide by 2. So, this will be total number of edges. So, if a k regular graph with n vertices are there, then it has nk by 2 different number of edges. Now, we are going to see a k dimensional cube or a hypercube structure. So, a k dimensional cube or a hypercube qk is a simple graph whose vertices are k tuples with the entries in 0 and 1, and whose edges are the pairs of k tuples that differ in exactly one position. For example, so this is the Q3. Q3 means here the vertices are represented by these 3 tuples 1, 2, 3. So, there is an edge between these 2 vertices, and they differ only in one bit or one place of these k values. Now, j dimensional subcube of a qk is a subgraph of qk isomorphic to qj. Now, above we show q3, so that I told you q3, it is shown over here. So, the hypercube is a natural computer architecture. Processors can communicate directly if they correspond to the adjacent vertices in qk. So, k tuple that name the vertices serve as the addresses for the processors. Now, let us see the theorem, which is quite simple theorem, and which basically can be proved also in a very simple manner. Quickly we will see that. Now, if k is greater than 0 or k is non-zero, then a k regular bipartite graph has same number of vertices in each partite set. Let us prove that. Now, if G be a k regular xy bigraph, then we can count how many edges according to their endpoints in x. So, if you see how many edges are there, so how many edges will be incident? K number of edges are there, because it is a k regular graph. So, it will be k times x. X means all the nodes which are present in this partite set x, that is Eg. Similarly, if we count how many edges are incident on y, so that also Eg will be k times the number of k times all the vertices. Now, edges are same, so k times x is equal to k times y, and k will go off. So, x is equal to the y, that means the partite set x is same as partite set y. So, has the same number of vertices in each partite set, hence the theorem is proved. So, this is the theorem which we have already proved that. Now, there are techniques which will be applied to for a counting. So, this is the example in which the Peterson graph, we can say that it has 10 6 cycles, and we can definitely can see this. There are 2 different ways we can draw the Peterson graph, 3 ways, and we can find out using claw that it has these many properties. Now, let us see some more extremal problems. So, extremal problems ask the maximum or a minimum values of a function over a class of objects. So, for example, the maximum number of edges in a simple graph with n vertices is n choose 2. So, that means if you see the edge in a particular pair of vertices uv, so out of all n vertices, every time you choose 2 vertices and place an edge, hence n choose 2 times basically you will be or number of ways you will be adding the edges. So, the maximum number of edges which can be placed in a graph of n vertices is n choose 2. Similarly, let us see the how many minimum number of edges in a connected graph with n vertices can be there. So, with every graph with n vertices and k edges, there we have proved earlier a particular lemma that says that it has at least n minus k components. So, that means with n vertices and k edges will have that many number of components. When you say a connected graph, that means the number of component you want to make it as 1. So, what is the value of k over here? K is equal to n minus 1. So, that means there are n minus 1 edges, minimum number of n minus 1 edges are present to make the graph having n vertices as connected graph, and if the number of vertices goes less than n minus 1, then it will be disconnected. The example of a graph having n minus 1 edges is called a path Pn. So, we can see this is P3. So, how many edges are present? 1 and 2. There are 2 edges are present and it has 3 vertices, n is equal to 3. So, number of vertices will be n minus 1, that is 3 minus 1, that is 2. So, 2 edges are present here in this particular graph. So, conclusion: in this lecture we have discussed Eulerian circuits, fundamental properties of a graph, vertex degrees, counting and extremal problems. In the upcoming lectures we will discuss further extremal problems, graphic sequences and directed graphs. Thank you.